Hi kids, Mr. Josephs here, and I'm going to tell you a little bit about how to do Lab 7, the Force Vector Lab. And the way we're going to do this is we're going to use a force table, and a force table looks like, let's see here, where's my thing? Looks like this. All right, you've got a ring attached to some strings are attached to the ring, and they dangle over pulleys along the side, and you hang masses off of each of these little pans that are right here, and they pull on the ring. And what we want to do is have 4 strings attached, and then that ring will remain suspended around the pin without touching the pin, and it will be at equilibrium. You're going to choose 3 different forces, and then you're going to calculate what the 4th force needs to be in order to bring the pin to equilibrium. And so let's see how we're going to do this. You're not allowed to have them lined up as nicely as shown here, so that it's a little more complex. So here's the directions. This lab is using the instrument called a force table. A washer is placed at the center of the force table, and then strings to the ring and hung over the pulleys, like you just saw. The magnitudes and the directions of each pull can be varied. And so you're going to do that. You're going to vary it. So until I get back, we're not going to actually use the force table. You can do this entire lab without using the force table. And so that's what you're going to do. You're going to choose, instead of hanging these, you're going to choose 3 strings and positions that you're going to position the strings at different angles, and it should look similar to what we did in this assignment from yesterday. So you would choose like 3 forces like this at different angles. The force table has a 360-degree protractor right on it. And so you would choose something like this, and then you're going to have to calculate where the 4th vector is going to have to be and what the magnitude of that will have to be, using the 2 methods that were also in this assignment. All right, so this assignment was to get you ready for the lab. So the masses should be different by at least 20%. And you shouldn't go any higher than, I'd say, 300 grams. I should have put that on here. I didn't have that on here because, oh wait, right here, 200 to 400 grams. Never mind, I did put that on there. All right. They have to be different by at least 20%, so show your calculations to show that you're choosing different masses by 20% differences. None of the angles can be within 10% of 0, 90, 180, or 270, and you can't choose anything that's within 10% of those as well. So you can't have an angle that's, say, 100 and then another angle that's 190, because you would have an angle, the difference would be obviously 90 degrees. So make sure to go through your calculations after you've chosen your 3. Now, you should probably have a data table set up to show your stuff. So the data table would be vector, so it'd be like F1, F2, and F3. Now, something that we're not doing here, we're not finding the resultant vector. We're finding the vector that will bring it to equilibrium. So we're actually finding the opposite of the resultant. The mass in grams, and then the direction in degrees. This is your data, okay? Now, how about data analysis? Well, data analysis we have to have these vectors in force unit. See, mass is just a scalar. Mass, when you are, let me show you the difference between mass and weight. If you have some object on Earth, this is Earth. Let's just have, we'll call it a rock. Mass is amount of stuff or matter in an object. Weight is a force felt by masses near Earth or any other planet. But so this has, at this position, we'll call it position A, this has mass and weight, because it's near Earth. But if this rock were out here, rock in space, we'll call this position B, this still has mass, but it doesn't have any weight, because it's not near Earth, and so there's no force pulling on it. So when we are looking at the data, we need to have the forces, the vectors, with its weight, which is its force. It needs to be in a force unit. That's just being consistent. Technically, it would work out if we didn't change it, but we really should to be consistent. So the vector, force 1, force 2, and it explains it also on the lab right here. Right here. The magnitude of the string tension is determined by the amount of mass which is hung from the other end of the string. The magnitude of the force in the vector is in a string is equal to m times g. That's mass times little g, where m is the mass in kilograms hanging from the string, and g is equal to 9.81 meters per second squared, or technically in this case it would be 9.81 newtons per kilogram, because force will be in newtons. And this number is given to you on the front of your reference tables. Alright, so the vector, you have the mass from the data that you choose. You're going to change the mass to mass in kilograms, which you should know how to do. And then you change it to weight force. Weight by m times little g. And then this will be in newtons. Okay, and these are the numbers. The newtons are the numbers you will use in your calculations, your algebraic calculation, and your diagram, your scaled diagram that should show everything on the force table like this, and then actually do the calculations, which I can show you for this particular one. Nope, 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 nope. R right here. So you'll have something like this, but here's like a head-to-tail method. The thing is that instead of drawing the resultant, which would go from the 0 out to the end of the third vector, you actually, to find the fourth vector, you would draw it from the end of F3 back to the tail of f1. And that's because this will create a closed loop, which makes the resultant vector on the entire thing to be 0. And that's what we want. We want it to be 0 because we want that pin to be not moving at all when we place these values on here. So make sure you go through and read each of these in detail. You can email me or ask me questions in a private comment if you have some questions. It leads you through each of these. Here's the graphical method, and then you have the mathematical calculation method or the algebraic method explained here as well. And then compare your results. When you have this finished, you should have this following lab format, just as we've been writing these lab problems up. Each person should have their own document attached to the lab assignment in Google Classroom. You have to write out the problem, which I wrote out right there for you. The procedure, how you would go about hanging them on the force table. You could skip that technically for now. This is kind of a different type of a lab. And then determine your three masses. Determine your three masses and your angles that you choose. And this is, you're not collecting any data from this lab, you're actually coming up with it. Do the data analysis like I told you, and then write a conclusion on how well those values came out to be. And then next week we will test to see if your 4 values work out perfectly. All right, this lab usually comes out to be pretty well. So if you need me to check your work before you start to do calculations to make sure that these requirements have been met, because if you do not follow these requirements, you will have to begin again, then you can always do that and leave a private comment and I'll check it. And then you can get to work on the calculations, which were very similar, again, to this assignment right here. It's not exact because of the difference with this. You are not finding the resultant, you're finding the vector that would bring this back to 0. Well, have fun, guys. Bye-bye.